with all the admin stuff. So start now. Okay, so I'm gonna present chapter 16 of the Fundamentals of Data Visualization by Klaus Wilke. This chapter is called Visualizing Uncertainty. So the topic here is how do we graph and how do we put uncertainty in graphs? So for that, we're going to review different ways to measure uncertainty and different ways to visualize that uncertainty. Okay, so first, the most commonly used approaches to visualizing uncertainty are going to be error bars and confidence bands. That's probably the ones that you guys have seen and used more often. There are a lot of ways to represent uncertainty, and that's going to depend on the type and knowledge of the audience we want to convey the message to. Because if the audience is, for example, a journal, a scientific journal, people that read the scientific journal, then they're going to probably understand what confidence intervals are. But if you're presenting to a less, I don't know if this is politically correct, but less educated audience, then that means that they're probably going to understand better if you present like a standard deviation or like a standard error, not necessarily something that has to do with distributions, right? So, or probability. So then that's also going to affect the one that you choose. But let's start first with understanding the concept of uncertainty. What exactly do we mean by that? So when we're talking about uncertainty, we usually are talking about probability. And what we're talking about here is the probability of something happening, of having a success over a failure, or having something, a certain outcome. It depends on what type of data we're dealing with. So for example, if we toss a coin, then we're gonna expect a particular outcome. Either we draw tails or we draw heads, right? So if we are looking at how many times we draw tails and we call that a success, then we can expect, for example, a probability of 10% of every time we toss a coin, we're going to draw tails. So that means that every time we repeat the trial, we are probably going to see that 10% of chances of having that result. So that means if we only do one experiment, that means we only see one outcome. No. If we have, I think these are 100 experiments, but if the probability of drawing a tail is only a 1% chance, then this is what that experiment is going to look like, the results. Just one tail drawn out of all of the 100 events that happened. 99 were tails, 99 were heads, and one was tail. But if we have a 10% of having that result, which would be tails, then it would look like this. And then 40% would look like this. That's our success. That's exactly what we're looking at. So that is uncertainty. How certain are we that we're going to get the result that we want or the outcome that we are expecting if we have a series of repeated events? So uncertainty only makes sense when we have those repeated events. It really doesn't make sense when we only have one experiment or one outcome or one point, right? We have to have several measures or several experiments or repeated events. And another thing to note here is that these waffle plots are really handy when it comes to visualizing probabilities as frequencies and to understand uncertainty when we are dealing with frequencies. Because I think we've talked about waffle plots before. When we have point estimates, we have to start first by reviewing a few key concepts in statistics. So we have to remember that when we're dealing with statistics and when we're dealing with repeated outcome or repeated experiments, sorry, that means that we're drawing samples from a population. It's very rare that we're going to take samples from the entire population. It can happen, but we usually work with samples. So then that means that we're going to have a population distribution for the variable that we're interested in. Let's say that this is height. We're going to have a mean and we're going to have a standard deviation of that variable of interest. So that's going to be our population distribution. This is how our population behaves in terms of, in this case, height. But then when we draw a sample, we're going to have a mean of that sample, which is not going to be the population mean, it's going to be the sample mean. And we're also going to have a standard deviation. I'm sorry, we're not going to have, well, we're going to have standard deviation, but it's going to be from the mean, but we're going to have a standard error associated with that sample. So then here we have to start understanding the difference between standard deviation and standard error, because I think, we are all very familiar with that. So the standard deviation and the standard error are completely different things, and it's very usual or very common for people to confuse these two terms. When I talk about the standard deviation, that's going to be a property of the population. So that's going to be associated with my population distribution, which is going to be a measure of uncertainty of that population. It's going to tell us how much spread there is among individual observations that we could make. And by contrast, the standard error is going to tell us how precisely we have determined a parameter estimate. So technically, we have a standard error for the mean. We could have a standard error for the standard deviation. We can have one for the variance too. But we usually show the standard error of the sample by showing these how precise our estimate is within the sample. So in this case, where is this? So in this case, the standard error is associated with the mean of our sample. So it tells us how precise we determined the mean of that sample based on the value of the population mean. If the standard error is too wide or the number is too big, then that means that we have a lot of uncertainty relating to how close our mean or sample mean is to the value of our population mean. The book starts to draw differences between how frequentist and Bayesian statisticians show uncertainty. So I'm gonna talk a little bit about that. First, I'm gonna talk about the way frequentists show uncertainty using error bars. And these error bars can mean standard deviation around the mean. So the sample, the point here, the orange point here is going to be the mean, in this case from this sample. And then we can draw these error bars around the mean showing the standard deviation. And we have to say if this is 1, 2, or 3 standard deviations around the mean. In this case, I assume it's 1 standard deviation away from the mean. Then we have the standard error that it's going to look like this. And then we can also use confidence intervals. So confidence intervals are different from the standard error and the standard deviation, but are also uncertainty measurements. So the confidence interval in frequentist or for frequentist statistics is the range of values calculated from the sample data that has a certain probability of containing the true value of the population parameter being estimated. And that it has a certain probability. This certain probability, it's going to be depending on if we're doing 80% confidence interval, 95 or 99% confidence interval. So that means that if we're using this 99% confidence interval as our way to measure uncertainty, that means that if we repeat the same experiment, if we draw these samples 100 times from our population, then we can be sure that in 99 times of 100, our sample mean, our population mean is going to be within these values. And then if we do it with like the 80%, which is why it's narrower, that means that if we repeat this experiment 100 times, so if we have this sample drawn from the population and we do this 100 times, 80 times of 100, the population mean is going to be included within these values, so within that range. So that's how a confidence interval is interpreted. And like I mentioned, it's usually shown with these error bars. However, it's not the only way. Sometimes, depending on what package you're using and what language, what you can have is at least the bar, but other people, what they do is they can show the mean and then different types or different levels of confidence intervals. So there's, and then they are shown here by color. So the one that's darker means 80% confidence level. And then the medium color is going to be 95%. And then the whiter one, which is the lighter color, is going to be 99% confidence interval. So that is another way of representing confidence intervals, is instead of just showing the bar, the error bar. This way, by using these three different colors and widths of the line, this is giving us the opportunity to present and compare three different confidence levels within one plot. So that's actually very, very handy. The other thing to notice or to note here is that the larger your sample size, the narrower your confidence intervals are going to be. Okay, another way that we can represent confidence intervals is by doing, which is the way I prefer to do it, but it depends because sometimes these three levels are also super handy. And I've also seen people use these different colors with the distribution plots. So this is another way of showing exactly that. And then the other way can be that that they are showing with different colors instead of showing them here with the lines. The colors can be inside the distribution, like the histograms, the density plot, sorry. And then you can have them like the darker color is going to be 80% confidence interval, and then they go with a lighter color for 90 and then 99%. Another way that I don't like this one, but this is another way that I've seen also represented, confidence intervals being represented, which is with this single interval error, but with like a gradient. Instead of being just one single line, it has like that gradient. Not my preferred way, but it's another way of visualizing data. And the error bars can have a cap or they may not have a cap. It's a preference. I mean, whichever you prefer. When we're talking about Bayesian statistics, what we do is we calculate posterior distributions and credible intervals instead of calling them confidence intervals, which is what frequentists do. So the names, it's CI when you abbreviate them. So sometimes that causes a little bit of confusion. So confidence intervals come from the null distribution, and the credible intervals come from the posterior distribution. So everything that has to do with Bayesian statistics have to do with distributions and with drawing thousands of samples coming from a distribution. So in Bayesian statistics, the posterior distribution is going to tell us how likely a specific parameter estimate is going to be given the input data. So if we are estimating a mean, for example, then that's what the posterior distribution is going to tell us. Instead of having one value, which is what we do in frequentist statistics, we are going to have a posterior distribution giving us a distribution of that possible mean instead of just having one value. And with that information, we also define the credible interval, indicating a range of values in which the parameter value is expected with a given probability, as calculated from the posterior distribution. So that means that we have the posterior distribution. So we are going to have a distribution for the mean. Let's say this, instead of having like the mean is 50, we're going to have a distribution of values representing that mean. That's going to be our posterior. And then we're going to calculate a credible interval, which is going to be the range of values in which that parameter, that mean, that sample mean, or that population mean, sorry, is going to be expected given a probability, which can be 95%, 80%, 99%, whichever we want to use. So that Bayesian credible interval is going to make a statement about the true parameter value, whereas a frequency confidence interval is going to make a statement about the null hypothesis. So it's going to tell you not just one specific value regarding the null hypothesis, or it's all about the hypothesis testing there, right? Whereas Bayesian is all about distributions. So again, the way that we represent those credible intervals can be again with error bars, or can be with the same way that I showed you before, essentially. When we have curve fits, or when we have like a line that represents a fitted line that represents, for example, a linear regression that we did for a data set, then the way we show distribution is going to be with a confidence band. And that is represented with gray here. That's going to be around the fitted line that's going to be right here in the middle. But that confidence band, the way that it should be interpreted is that it's going to give us a range of different fit lines that may be compatible with the data. So even though we see just one fitted line, which is the line that we have, like the equation that we essentially come up with when we do like a linear regression or a linear model, the confidence band that's going to be this gray area around this, what it's really given us is all the possible lines, all the possible fitted lines that we could draw that still would make sense with given the data that we did. So then that's why when we draw all those lines, it usually is wider around the edges, so here and here, but then it becomes very thin in the middle because all the lines converge there in the middle. So that is essentially what this is showing us, but we don't show it like this. We usually only show the band around the fitted line. And I didn't put, but I can show you in the book how that looks like, because I didn't put that one. Oh, shoot, where is that uncertainty here? So it usually looks like this. Or it can also be with the gradient colors that we saw before for 80, 95, and 99%. This is another way of seeing those curved lines when we fit a line that is not necessarily linear, but it's like a polynomial model or something like that. Then we will have again the band, the gray band, and you can show it in any color that you prefer. And that is just representing essentially all the possible fitted lines that can also explain the data. So then that's how we draw the width of the fitted line. And that's it, you guys. I thought this chapter was going to be longer, and that's why I only said, oh, I'm just going to do 16 and I'm going to leave 17 and 18 together, but no. So I'm not sure if anybody has any, I'm going to stop sharing here. Any comments or any things that you guys want to say?
Nothing much, but thanks a lot, Gabby.
Mhm.
I also thought it would be a much longer chapter, but yeah, I think you summarized it well.
Thank you. No, yeah, this one was very, very fast. I assume that everybody's familiar with the concepts of uncertainty, so maybe I should have explained those a little bit more, but I feel like we all know, right? Like standard deviation and standard error and all of those. Um, but yeah, essentially we work mainly with confidence intervals or credible intervals if you're a Bayesian. So I guess I those make more sense sometimes to use. Um, yeah. So I don't know if anybody else has any other comments or
Nothing really, just that I think I'm definitely going to start doing the um the different colors, like the gradient of colors for different confidence levels, because I think it really helps you intuit where the possible outcomes are actually concentrated.
yeah, I think they also look very nice. I think your plots look very fancy when you do that, but it does help you understand that. I have seldom seen those in publications, and I don't remember what the R package that does that, but I'm sure there is one. It just escapes my mind at the time being, but there is one, I'm pretty sure. I'll start looking into it and then I'll put that in Slack because there is
Yeah, I'm sure worst comes to worst, you could just kind of build it by just having multiple layers in your plot. But
yeah.
yeah, it's on my to-do list to go into the GitHub for this book to see how he does it.
Yeah, they do look nice for sure, and I think they are quite informative. I've also never seen them done anywhere else but here, and I think they are quite informative.
Yeah. I'm trying, I think, oh, maybe it's this one. Let me see. It could be this. Oh, I think it's this package ggdist. If you guys, let me put it in the chat. So if you do R, if R is your language, I think the package that does this different colors um, in the error bars, I think it's ggdist. I think that's the package.
GG list.
Yeah, I think, but I'm not sure.
Yep, I think it is. It's looking very much like it is.
Right. I think it's that one.
Okay.
I like these rain clouds too.
Yeah, it does rain clouds. Yes.
They're I could see how they would not be like ideal for the layperson, but they're cute.
Yeah, I think it's this one. Yeah, I'm gonna put the link here in the chat. Oh my God, I'm so glad that I remember because that is the one to go with. Yeah, and you have the rain clouds. Yes. Okay, we definitely need to explore that one in a different book club. Oh yeah, you put
Mm,
it too. Oh, thank you, Ashley. Aha, I put it after you. Yeah, that's exactly the one. Okay, you guys, so if there are no more comments, I guess we're done for the week. And let me fix the calendar, and I'm gonna talk to John about this. We'll fix the calendar and then we'll see if we do meet next week or if we don't. So yeah, so that's it. I'm gonna put stop in the chat and